Okay, folks, we'll start in about a minute. Just getting everything together. I did figure out my problem from last time about why I couldn't get the optimized bubble sort to work. We'll talk about that. That's one of the examples we're going to cover. Let's see. Okay, I've got 4 o'clock, and I know we've got Thanksgiving tomorrow. Everybody wants to get something done, so let's get started doing this. Today's topic is complexity analysis of algorithms, another computer science-y topic that's really important and which I have a history of not explaining very well, so I've totally revamped this lecture, and hopefully it'll do better. Administratively, Project 3. The data file, a number of people have had trouble getting the data file loaded. It's an encoding issue. There are different ways to encode the binary bits of the file, and it turns out that Jupyter defaults usually to expecting UTF-8. And so if you just use the read statement, and I'll show you exactly what I mean in a second, it can't read it. It tells you this is invalid for UTF-8. Specifically, the data file is encoded as ISO 8859-1, which is better known as Latin. So what I mean by that is that, hang on just a second. So I told you in the instructions to read in the file, the CSV file, the comma separated value file, using that statement. Just data frame is the variable name, equals PD. PD is the shorthand term I told you to call the pandas module. PD period read underscore CSV project 3 data.csv. If you get a very long detailed error, this particular error I'm showing now is a file not found. We'll talk about fixing that in a minute. If you get an error that said this is not properly encoded UTF-8, it'll be a bizarre error. You should use this line instead. And you notice it says data frame equals pd.read underscore CSV. Now I gave the full, if you're having trouble finding the file name, you can give it the complete path. When I say give it the complete path on my Mac, the data file happened at this point in time when I was running this notebook to be in my home directory, which on a Mac is Alfred Arsenal. On Windows or Linux, it'd be different. But on a Mac, that's my Alfred Arsenal directory. /download /project3 data.csv. What you need to add is encoding equals, and then in quotes, ISO 8859-1. That tells Jupyter that the file is encoded as Latin or ISO. It is not encoded as UTF-8. So if when you are running the original command I gave, which just said read file name, you get an error message saying, I can't read this UTF-8, then the way to solve it is to add this encoding equals ISO 8859-1, and that will tell it how to, that will tell Jupyter how to properly interpret, and Python can then read in. If you look at, if you want to check to make sure you've read in the file, already be confusing. If you just type data frame in a cell, it will print the entire file for you. It's a very long file. There are 3,421 lines of data. Now, since this is a CSV file, this is a comma separated value file. If you want to look at the data file yourself, you can open it in Google Sheets. You can open it in Excel. You can open it in Numbers if you've got a Mac. You can open it in any system like that, any application that does spreadsheets can read a CSV file, and you can look at it, in Google Sheets and say, okay, this is what it is. It's 3,422 lines. The first line is the header row, and then 3,421 lines of data, and I believe it's 18 columns. Okay, we're going to cut that way down. That's part of the Python coding you're going to do. If you want to see, after you've run this line and it worked without an error message, whether you've got it read in properly, you can type dataframe.head. Now, just dataframe by itself types the whole file. It runs forever. It's not a big deal. Dataframe.head by default shows you the first 5 lines and the last 5 lines of the file. That just gives you a real quick summary or a real quick snapshot. But I can see from looking at the result of dataframe.head that, yeah, this is the file as it's read in. It's done properly. Okay, so the file is there and this all works. So you don't have to do that. That's just something you can do to check for yourself that the file has been read in properly. If you want to delete a cell, if you want to put coding in to test, to check, you can always delete the cell later on by going up here to edit and clicking cut cells. And that way, I do that a lot. I'll put in some debugging code and test myself to make sure it's working right. And then I can cut that cell before I hand in the final program because it's unneeded. That's what you do. At any rate, dataframe.head, and you can see that, in fact, you can compare it to the Google Sheets format. You can see whatever, that this looks fine. One of the reasons for using pandas in this reads CSV is that it automatically takes care of that header row. Remember when I had you read in in Project 1, the data files with everything there, we had header rows, and you had to have this call to useless line equals read, file.readline. You don't need to do that with this. Pandas takes care of it automatically. It reads in that header row. It associates that header row with the file, with the columns, and gives it names. That's basically what this is saying, bound method.ndFrame.head. What it's telling you is that it has used the default method to determine that this is the header, the column header that goes with this column, and the header row has been thrown away. You don't have to worry about it. One other problem that a number of people have had, I told you to use Conda to install Plot9. If you are having problems with Conda, we had more problems with pip than Conda, so please try to use Conda. If you are having problems installing Plot9 using Conda, try pip. And the way that is, I just took a cell in Jupyter and I typed pip install Plot9. If you install Plot9 either through pip or Conda, it loads a lot. It's really nice. It takes care of all this stuff automatically for you. It takes some time, and it prints out all these statements. And don't worry about this. Not a big deal. You can use pip to install Plot9 if you're having problems with Condas, but try Condas first. I think those are the major administrative notes so far. Oh, we'll get to one other one in a minute. The data files encoded as I said that. I told you in the cells where you're running quick sort and selection sort to decide which is faster, use time.time_ns. You have to have an import time. You have to import the time module in order for that to work. I realized I didn't explicitly state that in the instructions. We're actually going to do that to demonstrate some of this analysis in today's lecture. So I'll show you how to do it, and I'll mention it that this is the same thing you have to do in your program. So those are the notes I've got right now. Again, if you have questions on the homework on the project, let me know, because we need to be moving along. You've got 9 more days, which should be plenty of time. And the coding is really not that hard once you get going. It's just making sure you get yourself started. With that being said, let's talk about analysis of algorithms. Apologies, I run them all together. And we're going to focus this on sorting and searching algorithms that we've talked about, but really this applies to almost everything you do in Python and any other language. Okay. We talked about 2 ways to search through a list. I got a long list and I want to look for a specific value. Linear search starts at the beginning and checks every element in the list and stops when we find it, or goes all the way through every element of the list and says, didn't find it. If the list is already sorted, either high to low or low to high, then we can use binary search. We talked about that, which is we just go right to the middle of the list and check that element. And depending on whether the item we're looking for is less than or greater than this middle element, if it's equal, we stop. Hey, we got lucky. Some people win the lottery. It happens. If it's less than, then what we do is we, if the list is sorted, we binary search recursively with either the left half or the right half of the list. In other words, in binary search, we divide and conquer. We check the middle element. We then recheck on the left or the right. We check that middle element and keep going until we either find it or we know it's not there. But again, binary search only works if the list is already sorted. So sorting a list is important. We talked about 3 algorithms to sorting a list into order: bubble, selection, and quick sort. And I mentioned Monday that quick sort's the fastest, and I'm going to talk to you tonight about what that means. I'm also going to fix my bubble sort explanation was not really good, so I'm going to hopefully fix that. But first, I'm going to talk about this whole notion of analyzing algorithms. Why do we care? I mean, the algorithm works, right? It gives me the right answer. If it doesn't run fast, why do I care? Hardware is cheap. It's an excuse to buy a new server. It gives me an excuse to buy a GPU, a graphical processing unit, that helps accelerate things on my computer. GPUs are great not only for gaming, but for doing things like Bitcoin mining and other cryptocurrency stuff. No, please don't do that. But GPUs are really nice. So if my program doesn't run fast enough, buy some extra hardware. Cool. That's an excuse. Clouds are even cheaper. Okay, and you get into the higher level classes, what they do is you just go on to Amazon Web Services, AWS, which is the Amazon cloud, Microsoft Azure cloud, or the Google cloud, whichever, right? Just run it on the cloud. The basic unit of computing on Amazon is called EC2, Elastic Computing Cloud. Hey, just go to Amazon, pay them a couple of bucks, buy an EC2 instance. If your algorithm's not running fast enough, buy a bigger one. Who cares? The reason we care is some problems are so intractable, so hard to solve, that you just can't solve them by buying hardware or using bigger cloud instances. I can't throw money at it and solve it in any reasonable way, not even Elon Musk or Bill Gates or Jeff Bezos. So we need to understand that we have the best possible algorithm for solving this problem. We have to have the algorithm that works fastest, and here's a buzzword, costs. We have to have the algorithm that costs less. Now, since I use the term costs, I have to define what I mean by cost. When I talk about the cost of a program or an algorithm or something else, what do I mean? Am I talking about money? How much money do I have to pay Amazon, or how many CPUs do I have to buy, or how much GPU do I need to buy to run it? That turns out not to be a useful measure. Cost in money generally is not a useful measure because guess what? Wait 2 weeks, cost comes down, we're good to go. Especially this time of year with Christmas and winter holidays coming up, costs will go down next month and then it'll go down again in January. Am I talking about how much memory it takes to run it? I could be. I could be talking about how much memory it takes to run the algorithm. But again, memory's cheap. You know, I'm sitting here with multiple terabyte hard drives that I don't need anymore. So memory is not particularly useful. Do I talk about how much CPU time it takes to run it? Well, that's not a good measure because what kind of CPU? The Intel CPU that powers my Mac, the Intel CPU that powers my Windows box, the ARM processor that powers my iPhone? I don't know. So none of these is very useful. So when we talk about the cost of an algorithm, what I'm telling you when I say cost is it's a count of the number of operations performed in the algorithm. Now, what operations depends on the algorithm, But for the things that we're talking about today, we're going to count the number of comparisons of two list entries. How many times are we going to compare two list entries against each other, or a list entry with a target value? How many times are we going to swap two list entries in this sort? So that's what we talk about. When we say cost, we mean how many times do we have to do a comparison? How many times do we have to do a swap? For algorithms like searching or sorting, we care about these things like comparisons and swaps. So here is an updated version of the iterative bubble sort algorithm we talked about on Monday. This is fixed, okay? This is the while loop form, and what this does is it will bubble the largest value in the list up to the last element in the list each time through, and then it will cut one element short. It will go through one element fewer every time, and ultimately it will give us a sorted list with the highest value last and the lowest value first. Now, when I say bubble sort can be short-circuited, it's a little bit more efficient than selection sort because I can stop bubble sort if we're done early. If it's the case that my list is sorted the first time through, then I don't need to continue bubble sorting every sublist. I don't have to keep checking over and over if I'm already done. So what I'm doing is I changed my first for loop in Monday's code. This while I greater than 0 was a for loop. I changed that into a while loop. I used a Boolean flag called swaps. I set swaps to true so the list will run, so the loop will run through at least the first time. But then after that, if nothing is swapped, if the list is already sorted, swaps becomes false. I made no swaps. This is a false thing. And I could stop and return. So this is the code that we're going to instrument. We're going to count the number of comparisons, and we're going to count the number of swaps with lists of different lengths. And we're going to look at how much time it takes. Now, again, to clarify, this statement right here, if numbers sub j equals this is a comparison. I'm going to count the number of times this gets executed. These three statements collectively make up a swap. I'm going to count the number of swaps. Now, I will always have a comparison, but I may not have a swap that goes with it. So those may be different. I'm going to talk about ops, and I'm going to talk about time. So let's go to PyChart. Okay, here is the code I just showed you, the iterative bubble sort of a list of numbers. Again, I'm just going to use lists of integers because it's easier that way. Now, when I mentioned for project 3, you need to import the time module. That's just doing this. Import time just means that I now have available to me the time module. Okay. So now what I'm going to do in my bubble sort, first I'm just going to use time. Okay. When I start the routine, I'm going to insert a statement that says start equals time dot time underscore ns. Right before the return, I'm going to say, now this will probably get me all kinds of trouble for not, there we go. End or finish equal time dot time ns. Now, what this statement does, time underscore ns, the computer has a clock. All of your computers have clocks, and they count seconds, billions of seconds. Okay? And so since an epoch time, we won't go into detail, we're just going to use a difference here. Before I return numbers, I'm going to print elapsed time equals finish minus start. Okay. In other words, what I'm going to do is I'm just going to count the number of nanoseconds it took to run this. So let me see if I've got an indentation problem. Let's copy this into a console, and I think I will have an indentation problem. Let me see if I fix it. Yep. Let's see if I can fix that. Okay, let's see if that solves it. Let's see. Okay, let's see if that fixed it. Okay, so now we're all set. We've got this function defined. So what I'm going to do is I'm going to define a list. L equals the list of 9, 8, 7, 6, 5, 4. And I'm going to say J equals iterative bubble sort of L. Now notice, because of my code, that it took 19,000 nanoseconds to run the loop. That's how long it took in terms of time. And we're going to compare that to other algorithms later on, but that will give you an idea of how long this takes. It took 19,000 nanoseconds. It's a very small fraction of a second. If you use time in just seconds, which is the default, this will give you 0. So that's why you use nanoseconds. This, by the way, is what I want you to do in Project 3. So you'll have some statement before you start the loop that says, give me the nanosecond value at the beginning, give me the nanosecond value at the end, calculate the difference, and I can tell the difference in time between beginning and ending. Okay, that's all fine and dandy. That's useful for now, but I don't have anything to compare this to. I don't know whether 19,000 nanoseconds is a lot, a little, faster, slower. So I want to do something interesting, more interesting. I'm going to comment out my time code. So I don't want that anymore. And I'm going to count the number of comparisons and the number of swaps. So I'm going to count number of comparisons. I'm going to start it at 0. And the number of swaps, I'm going to start at 0. Okay, those are going to be the variables I use to calculate the number of comparisons. Now, note that I'm always going to do a comparison regardless of which of these is bigger or smaller. So what I need to do is I always need to increment the number of comparisons. The reason I did this before the if statement, I could do it later on as well, but I need to make sure that I increment the number of comparisons every time I do a comparison. Regardless of whether this is true or not, regardless of whether this code gets executed or not, then I always need to increment the number of comparisons. Now, only when I'm down here in this loop am I going to increment the number of swaps. So now what I'm going to do is come down here and print comparisons equal number of comparisons. Then I'm going to print swaps equal number of swaps. And then finally, I can return. Okay. So we're going to use this code rather than that. And hopefully I don't have an error in it. I don't need to import time because I don't use time anymore. Okay. So now we're going to start with the same list we did before. And we're going to run the same call. And now we should see how many comparisons and how many swaps. It took 15 comparisons and 15 swaps to run this. Okay. Which is interesting because it meant that it took, I had to swap every time through, which you can see that's bad luck. But yes, since this was in exactly the wrong order, I had to swap every time I made a comparison. So that's not a big deal. Let's switch this a little bit, though. Let's make it 6, 7. Now let's bubble sort that one. And this time I saved a swap. I had 15 comparisons and 14 swaps. So we had 15 comparisons on a list of length 6. Now, suppose I did this. I'm going to import random. I'm going to say L. Never mind. We'll get back to the lecture. I'll get back to that in a minute. With longer ones. Okay. The bottom line is it took 15. What I want to do here is I'm going to create an arbitrarily long list. L equals for I in range 1000. L dot append random dot rand int 0 to 100. And I just randomly generated a list of length 1000. Now let's go back to J is iterative bubble sort. Now we're going to bubble sort this list that's length 1000 long. And hopefully I won't totally destroy everything because this is going to take a while. We can now see why that happened quickly. It took 499,000 comparisons and 253,000 swaps to sort this array, this list of 1,000. Okay. So the numbers get pretty big pretty quick. Now let's go back to the slides and do some more analysis. So for this slide, I mentioned we did nanoseconds. It'll tell you a difference. For this slide, we talked about instrumenting to count the number of comparisons and the number of swaps. In general, when we report algorithm costs, we talk about what an algorithm costs, we don't use time. We can measure time. Time is important. Time is important because we need to know whether or not this algorithm will actually finish sometime in the known universe. Okay? But in general, we care about the number of operations. And the number of operations is going to be a function of the length of the list being operated on. What this means is I had a list of 6. It took 15 comparisons. I had a list of 1,000. It took 499,000 some odd comparisons. If we say the list has n elements, the list is of length n, then the number of operations, the number of comparisons and swaps and everything else is going to be some function of the length of the list being operated on. Now, it's a different function for every algorithm, but it is a function. Okay, so the algorithm cost in terms of operations is a function of the length of the list n, And so we're always going to report algorithms as a function of n, the length of the list. Now, let's be real again. Even in a list of a few thousand elements, right? Even in a list of a few thousand elements, we don't care. You saw how fast Python could on an old Mac, and literally this Mac is 6 years old. On a 6-year-old Mac, it was trivial the amount of time it took to sort a list of 1,000 integers. We don't care. But when the list gets to be in the millions or the billions or the quintillions, now all of a sudden the cost in terms of the number of operations becomes important. And that's why we care about this. Okay? I will go back just a second and show you one thing. Now, in this code, instead of for I in range 1,000, I'm going to see if this Mac will let me do, this is 10 million. Let's see if it'll let me generate a list of length 10 million. This is working. What's going to happen is that it can't be sorted in time. And I'll get back to that and see if it actually finishes. This sort, if I got that list of 10 million generated, the sorting of that 10 million would certainly not be done before class was over. And it probably wouldn't be done till later tonight, and so I'll kill it. So that's what we talk about if I've got lists of millions and millions and quintillions. And literally, if you're Twitter or you're Facebook or if you're Google, you care about quintillions. You care about quintillions of things per day or per month. When we do analysis of algorithms, we get to take shortcuts because we're computer scientists, we're geeks, we're lazy, we cheat, whatever. We follow a rule. Do not sweat the small stuff. Don't care about round-off error. I don't care about small things. In some cases, here's a thing in bubble sort. We can tell that the number of operations is a function of, say, n squared plus some function of n plus some other number, some constant. Okay. In math terms, go back to algebra, go back to calculus. F of n equals a of n squared plus bn plus c. Okay. So some constant times n squared plus some constant times n plus some constant. That's how many operations it takes for a list of length n. Now, here's a clue. Again, we don't care about hundreds or thousands. We really don't. You know, I can sort a list of thousands instantly. But if n is 1,000,000, think about this. If n is 10 to the 6th, n squared is 10 to the 12th, n squared is 1,000,000,000,000. If I have to do something 1,000,000,000,000 times, I'm never going to notice the 20 million or the 355 operations. I'm just not going to notice it. If n is 1,000,000, if I have a list of 1,000,000 objects, everything on how long it takes, how many operations, what the cost is a function of this n squared. This is very, very tiny round-off error. Okay. I've got an example in here that if this is 1,000,000,000 and this is 1,000,000, then this is 1,000,000,000,000, 1,000,000, which, trust me, rounds off to 1,000,000,000,000. You simply don't care. So when we talk about the cost of an algorithm, we are only going to talk about the highest power of n in the function. Here, even though this is the true summary of what it takes to run an algorithm, we're only going to talk about the n squared term. We're just going to ignore this because it's too small. That's what I say by don't sweat the small stuff. Don't sweat the small stuff because these terms are not going to be measurable. We're simply not going to care. We're just going to care about this first one. Okay. Now, we often, not always, but often will also get rid of this a, this factor times n squared. You may think it's cheating because it makes a big difference over whether a is 0.5 versus a is 100. And I agree with that argument, but the reality again is if n is a huge enough number, it just doesn't matter. It just doesn't matter whether it's 20 or whether it's 0.5. 20 versus 0.5, I can solve with some hardware. 20 versus 0.5, I can solve by getting a bigger cloud instance. Okay. A trillion, I can't. So we usually do also get rid of A. We will not always, but it's most often in the noise. It's a round off error, so we just let it go. I'm curious, did I ever get my, hey, I got my list of 10 million. Now, here's the real ugly. Let's get this sucker started. It, in all likelihood, will not be finished. I'll have to go to a new console and hopefully won't drag my computer down, but just give you an illustration of how big this can be. When we talk about analysis of algorithms, before we get to the answer, the last thing we need to talk about is, realistically, this is probabilistic. Okay, there's a probability at play here. I cannot tell you exactly how many comparisons and how many swaps. Think about the array, the list that was completely backwards sorted versus the list where a couple things were in the proper order. And I had different numbers of swaps, and I had different numbers of, I think I had the same number of comparisons in that case, but we had different numbers of swaps. So there's a probability factor in here. We have to go into our statistics classes and think about what the likelihood is. Okay. Easy example. We're searching. We're searching for an item in a list. You stop when you find the item. I mean, because after all, it makes no sense to keep searching after you found it. So if I'm searching a list for an item, my best case is I win the lottery. I find the item I'm looking for the first time. And how many operations does it take to search this list? One. Exactly one. That's my best case. Well, that might not happen very often. I might have to search every doggone item in the list, every single one, either because what I'm looking for is not there at all, or I just happen to find it as the very last element. That's my worst case. The worst case is how many comparisons, how many swaps, how many operations do I have to have before I find something in the worst case. Now, I can go back to my laws of probability. I can go back to my statistics classes. Remember how earlier this semester we calculated the arithmetic mean. What is the mean? What is the average? What is your expected value of how many operations it takes to find this particular item? Okay. On average, if I'm searching linearly, an item at a time through a list, I'm going to find it halfway through. Okay. Sometimes I'll find it the first time, sometimes the second, sometimes the third. On average, if there's a true random distribution of items in the list and a true random distribution of items I'm looking for, on average, I'm going to find it halfway through. So for every algorithm, I have a best case, a worst case, and an average case, and those become important. We'll get to it. Here is a 120 element list. Okay. I randomly generated 120 integers between 0 and 100 using random.randint. Okay. How many comparisons does it take me to see if the number is 83? The number 83 is in the list. I want to search this list linearly for 83 and see if it's in there. Well, there's 1. There's 2. There's 3. There's 4. There's 5. We're not going to waste our time going through this. 83 is not in that list. So the answer is I will have to check every single item in the list, every single list element, and it's going to take me 120 comparisons to search this list. And then I discover, sorry, not there. Now, what if I'm searching for 22? How many comparisons does it take me to find 22? Found it. We're good. So best case, I happen to be looking for 22. I find it the first time. Worst case, I'm looking for a number that's not there. 71 doesn't count because there are other instances of 71. But in a different list, it might be. But I'm looking for a number that's not there. 83, for example. It takes me all. So that is best case, worst case. Best case, 1. Worst case, I have to look at every single element. That finally gets me to big O notation and how we report algorithmic efficiency, how we report how good an algorithm is. It's called big O notation. Use a capital O, an uppercase O. This is not a zero, it's an uppercase O. And I say, and O stands for on the order of, or order of. When I describe how long it takes an algorithm to execute in the worst case, how many comparisons it takes, as I said, I use big O and I go in terms of N, and I go in terms of the biggest size of N. Linear search, we report as O of N. Okay. Why? Because in the worst case, I have to check all N elements. There's a little bit of cruft I have to do extra. So it's actually N plus a few things. But again, we don't sweat the small stuff. If that list was 12 million elements long instead of 120, the few other statements in our program don't matter. Linear search is O of N. What that means is the number of operations we're going to have to do to search a list linearly in the worst case is O of N. Now, if I want to report the best case, I use the Greek letter omega. Okay, this little horseshoe thing, hopefully you've all seen it by now in your math, science, or even in other things in school. This is an uppercase Greek omega. The lowercase looks like a little W. Big omega says, what is the best possible case for this algorithm? Now, in this case, we've already said the best possible case for linear search is 1. Okay, so we report that linear search is omega of 1. The best possible case for linear search is 1 comparison, and we're done. The worst possible case is N comparisons. Now, in both the N and the 1, your program has other stuff that you have to look at, but we don't care. That's all round off. We ignore it. We don't sweat the small stuff. So linear search is big O, worst case, of N. And it is omega, best case, of 1. Now, you will find as you move through that most people care about O rather than omega. But omega does exist. One other point. The way we teach it in this class, big O is worst case behavior. You will find others who say that big O should represent the average behavior. And that's going to be important when we talk about quicksort in a minute. Okay, so in this class, big O means worst case behavior. Other people will tell you big O means average behavior. Apologies for the confusion. The community has not settled on that. I'll talk about where it's important later on. For now, for CompSci 201, big O is worst case behavior. Now, binary search. Okay, suppose I had a sorted list. What is the best case? Well, the best case is still 1. Okay, I have a sorted list. The first element in binary search I'm going to check is the element in the middle of the list, halfway through. That may be the element I'm looking for. I mean, people win the lottery. It's not often. I wouldn't, set up a retirement account that way. But there is a best case of 1. You can find the element you're looking for on your first search. It can happen. So binary search is also omega of 1. But worst case of binary search, you're not going to check every element since the list is sorted. You're going to check the one that's in the middle, and then you're immediately going to throw away half. Then you're going to check the half of the list that you think might contain the value you're looking for. You're going to check the middle value. You're going to throw away half of the remaining list, or a quarter of the original. Now you're down to checking a quarter of the original list. And on and on. The worst case, again, in a search is that you don't find the item you're looking for. You can't stop because you don't find it. The worst case for any search algorithm is always going to be, I don't find it. In a binary search, that worst case is the base 2 logarithm of N. Okay, that means that the number we're looking at is going to be the power you raise 2 to get n. If this is a 1024 element list, it would help if I had the fingers on the right keys. 1024 is equal to 2 to the 10th. Okay. You should know that. Any computer science, 2 to the 10th is 1024. And we just call it 1,000. We call it a K. So if I have a 1024 element list, that says I'm going to take at most 10 comparisons to find out something is not in this 1024 list. Okay? So log 2 of n is just the number that you raise 2 to that power to get n. So if n is 1024, there's 1024 elements. 1024 is 2 to the 10th. So the log to base 2 of 1024 is 10. And therefore, I know that on the order of 10 comparisons will let me go through the entire list and determine that, no, this element is not there. So we can see that log of n is a lot smaller as n gets bigger than n is. So binary search is going to be a lot faster if the list is sorted than is linear search. Best case, it's still 1. There is no difference in best case between binary and linear. It is still 1. Okay? So we don't really care about best case. Again, don't bet your retirement on winning the lottery. Let's, try to do this reasonable and take into account that we might have some hiccups. Let's put enough savings away. So binary search in worst case is better than linear search. Now, what about average case? Well, again, linear search, on average, you're going to find the item halfway through. And so average case for linear search is n over 2, or 0.5 n. So the linear search average case is 0.5 times n. And remember what I said, we throw away that factor a times n. So linear search average case is still just O of n. That's 0.5. Binary search is the same thing. On average, if the item's in the list, you're going to find it halfway through your search. And so your average case here for binary search is 0.5 times the log of n, which is still O of n. Okay, so average case is similar to the search to the worst case. It's O of log of n, okay, for binary search. So worst case and average case, binary search is going to be faster. So if my list is sorted, I am not going to use linear search. I'm going to use binary. Cool. Now the sorting algorithms. We'll go back and look at the code in a minute. The list is n elements long. I have to go through all the remaining unsorted elements of the list each time. I look at n elements the first time, n minus 1 the second time, and so on. This is equal to n times n minus 1 over 2 from your calculus class. Let's go to PyCharm and illustrate. That has not worked. We're going to kill that because otherwise my computer will never run again because it's still trying to sort that 12 million, that 10 million element array, and trust me, it's not going to finish. We'll start with a new Python console. Let's start again with my iterative bubble sort code where I'm counting comparisons and swaps. Let's set the list equal to 1, 2, let's go backwards. 6, 5, 4, 3, 2, 1. And now we will print iterative bubble. Let's just do J. I don't need to do the print. I've got the J equals iterative bubble sort of L. Now, how big was the list? What was the length? 6. N is equal to 6. Okay. N here is equal to 6. So the number of times we ran through this loop, this while loop, for now, let's assume this swap stuff doesn't happen. Everything is worst case. We run through the loop. We first run this when length of numbers minus 1 is 5, right? We're going 0 to 6. Length of numbers is 6, so minus 1 is 5, so I is 5. So we run this when I is 5, 4, 3, 2, 1, and so on. So we run through this loop 6 times. Now, every time we run the inner loop, every time inside this outer loop that we're going to run 6 times, in the worst case, every time we come in here, we have to go J to range I. The first time through, remember, I is 5, so we run J 0, 1, 2, 3, 4. Okay, 5 times. Actually, I times, because it starts at 0. Okay. So the first time through, we're going to run it 5. Then we're going to run 4. We're going to run through. Any rate, what we're going to do is we find that this statement that does comparisons, the first time through runs, sorry, let me try to clarify this. This is what I'm talking about. This is going to run 6 times the first time through, then 5, then 4. Now, we remember from our math class that any number n times n minus 1, or the sum of 6 plus 5 plus 4, go back to the slides, sorry. We remember from our math class that you go through n elements the first time, n minus 1 the second time because one element is already sorted, n minus 2 the second time, the third time because the last 2 elements are sorted, n minus 3 the next time because 3 elements are sorted, and so on. So the number of times we have to go through this and do comparisons is n plus n minus 1 plus n minus 2 plus n minus 3 plus n minus 4, and so on down to 1. Well, this is where our calculus classes comes in. The summation of n plus 1, n minus 1, n minus 2, and so on happens to equal n times n minus 1 over 2. Okay. That's just the, how to sum the series. That's equal to n squared minus n over 2. I just distributed the n across this. Or if I want to, this is 0.5 n squared minus 0.5 n. Now, again, we don't sweat the small stuff, right? 0.5 n squared minus 0.5 n. We clearly get rid of this term because as n gets big, we don't care. And we're also going to ignore the 0.5. So we say that bubble sort in the worst case is O of n squared. And so you will find that bubble sort is order of n squared. Okay, n squared operations. Now, it may be hard to understand that when I had, when I ran the case of 6 lists or 6 items in the list, I had 15 comparisons and 15 swaps, so that's 30, and 6 times, 6 squared is 36. So yeah, 30 is kind of close to 36, but maybe not so much. But okay, I'll buy order of n squared. But when I had the list of 1,000, okay, it took 500,000. Well, 1,000 squared is 1,000,000, so it took 499,000 some odd comparisons to do the bubble sort at and that's a half of n squared. And we can see that as we get to bigger and bigger of n, we get to something that truly can relate to n squared. So we say this is an asymptotic analysis to something you probably have seen in calculus or whatever. Asymptotically, as n gets larger, bubble sort is going to take n squared in the worst case operations to work. Now, best case is O of n is omega of n. The best case for bubble sort is omega of n. If the list is already sorted, let's come back here and say the list M equals 1, 2, 3, 4, 5, and 6. And now K equals iterative bubble sort of M. And hopefully this works right. It only took 5 comparisons and no swaps. The list was already there. So in the best case, the number of operations is just proportional to the length of the list. I had a list of 6. It took 5 comparisons plus some other stuff. No big deal. So the best case of bubble sort is omega of n. That means if the list happens to already be sorted when you pass it into bubble sort, we won't waste time. It's omega of n. So bubble sort is O of n squared, worst case, omega of n, and you'll find the average case is going to be still O of n squared. Okay, it's probably about a quarter of n squared, but still O of n squared. Don't sweat the small stuff. This is an explanation of what I just did. How did we round off 0.5 n squared minus 0.5 n? How could we just said order of n squared? 1,000,000 is a trillion. Okay, so when n is 1,000,000, a trillion minus 1,000,000 divided by 2 is 999 divided by 2. Rounded off to a trillion, it's close enough. You know, we could argue about whether we should really get rid of the 0.5, but okay, that's fine. All right. Selection sort. Not going to go through this much. It's almost like bubble sort, except that you cannot shortcut selection sort. We can go through the code and show it, but here's what you need to remember. You must go through all remaining unsorted elements of the list each time. Even if the list is already sorted, you cannot know that with selection sort. You know, with the code I gave you for bubble sort, we kept track of whether something's been swapped or not. You cannot do that with selection sort. So, selection sort is O of n squared, but the best case is the same as the worst case. Selection sort is omega of n squared. Now, there's another Greek letter, theta. If O and omega are the same, then we say the algorithm is theta. And that tells anybody who's using the algorithm, this is what you're going to get. Selection sort is theta of n squared. Sorting a list using selection sort is going to take something on the order of n squared operations, and there's a darn thing you can do. It doesn't matter how good your luck is running. You may have the winning lottery ticket, but you're still going n squared times. Okay, so theta means O and omega are the same, and selection sort meets the bill. O and omega are the same. The one that's interesting and the one that's fastest is quick sort. Now, there is a factor of probability in quick sort. Remember quick sort, we pick a pivot. I showed you a video where I think they picked the last element as the pivot. In my algorithm that I handed you last Monday, in the algorithm that's in Monday's code, I picked the first element as a pivot. Either one, it doesn't matter. Here's the bottom line. We have no way of knowing when we pick the pivot how many elements are going to go to the left, how many elements are smaller than the pivot, and how many elements are going to go to the right, how many elements are bigger than the pivot. That is just luck. There's a probability factor there. If we get really, really, really unlucky, every time we pick a pivot, it's the smallest number or it's the biggest number. The result being that when we pick a pivot and we sort left and right, everything goes to the left or everything goes to the right. And all we've done is make this a glorified selection sort. We haven't made anything faster. So if we have incredibly bad luck, if everything goes as wrong as it could possibly go, then quick sort is going to be O of n squared, okay? Just like the other two algorithms. Now, I will warn you, if you talk to most computer scientists and say quick sort is O of n squared, they're going to sympathetically tell you that you're wrong. They're going to tell you, wow, somebody's got an alert going. They're going to sympathetically tell you that, in fact, quick sort is O of n times the log base 2 of n. That is a probability factor. This is okay. Assuming everything here is just random and nothing is deliberately set out to mess us up, what happens is that on average, when we pick a pivot, we'll throw about half the elements into the left side, into that list I called less on Monday. We'll throw about half the elements into the right, that list I called greater on Monday. So on average, when we pick a pivot, we're going to get half to the left and half to the right. So when we recursively call quicksort on the left and on the right, we're doing so with a list that's about half the size of the first one. This is our average behavior with just everyday luck. So that's what we've got with quicksort on average. If you go through the math, then it's sort of like binary search. How many times are you going to go through about log n? In other words, if we had a list of 1024 elements and we sorted it using quicksort, we were going to call recursively about the log of n, or 10 times. We'd have to have 10 recursive calls to sort our list of 1024, but then we have to check every one of these 1024 algorithms. So on average, a lot of people will tell you that quicksort is O of n log n. And in fact, quicksort's average behavior is on the order of n log n. Okay? So remember, it's confusing. I apologize. I will do nothing to trick you at all on the final, but there will be stuff about analysis of algorithms on the final, but I'll do nothing to trick you. The specific description is that in 201, we teach you that quicksort is O of n squared because indeed, in the worst possible case, where you pick the worst possible pivot every single time, it can take you on the order of n squared operations to sort using quicksort, because your recursive calls are just a call with one element less. So in the worst case, quicksort is no better. But in the average case, quicksort is a whole lot better. N times the log base 2 of n is much, much less than n. And you can go through and plot a graph of it and see that it diverges. They get farther and farther apart. So what the exact performance is in quicksort just depends on how lucky you are guessing the pivots. But it turns out that on the average, it's n log n. The best case, if you look at it, is that it's omega of n. If you get a list that's already sorted and you quicksort it, then you will, in fact, run something on the order of n operations to decide that the array is already sorted. It's sort of like bubble sort in that particular way. So quicksort is a common algorithm. It is used a lot. It was a brilliant deduction when it was come out with back in the like 1950s or maybe early 60s by a Dutch gentleman named Dr. Edgar Dijkstra. It's an amazing algorithm. It is faster in almost every case, but you can get unlucky, and it can give you, this degenerate behavior of being order of n squared. Okay. So what did I do? Sorry, I've got a dog who wants his dinner begging me right now. On the average, you're not going to randomly pick the worst possible value for the pivot every time. Sometimes you're going to have good luck. In that case, half becomes binary search, and that's why I said quicksort is O of n log n. And that is all I have for tonight. And so you get out for Thanksgiving 10 minutes early. I hope you all enjoy your long weekend. This video will be up there. I'll be available off and on during the weekend. If you ping me by email, if you ping me on Discord, I will do my best to get back to you. It's not like we're having a big family gathering or anything. Neither are you. I apologize for that, but it's the world we live in today. So thank you all, and I will talk to you next Monday and get that project done. Thank you.